Hi, this is Chapter 3, Control Volume Analysis Part 3. In this video I'll be talking about two different types of analysis, two different approaches really. One is a control volume approach and one is a systems approach. And we'll talk about how in general in fluid mechanics we generally want to use a control volume approach. Then we'll talk about something called Reynolds Transport Theorem, which I'm going to show as RTT. And what Reynolds Transport Theorem allows you to do is to rewrite some of the basic laws like F equals ma, Newton's second law of motion. For example, we can rewrite that for defined volume in space, which is what we call a control volume. Now at this point I should mention that for industrial engineers and for mechanical engineers, some of this will be a review because industrial and mechanical engineers have taken Mech 309, a first course in thermodynamics. But I noticed that the biomedical engineering students do not get a course in thermodynamics, so I'll spend a bit more time talking about the difference between a system and a control volume for the sake of those students. And so down at the bottom of the image I've shown, of the page, I've shown three images with three different control volumes that the user might select in analyzing a system. On the far left-hand side here, I have a dashed line drawn around a nozzle. So we have fluid flowing in from the left and accelerating as it flows out the nozzle. And we draw a dashed line to indicate that's the volume that we're going to do our analysis on. And the outside of that volume, of the control volume, is the control surface, just so you get used to some of the terminology. And we're going to do an analysis on this very problem to figure out later on what the forces are required to hold that nozzle in place. Another example might be drawing a control volume around a ship and looking at the forces on the edge of the control volume and the flows in and out to analyze the drag on a ship. Or on the far right-hand side here, I've shown a dashed line inside the piston of an engine. The user might pick that kind of control volume if you're doing an energy analysis of a piston in an engine. So I'm going to start by really defining what a system is and what a control volume is. And these definitions come from thermodynamics. A system is a fixed quantity of mass. It's a collection of matter of fixed identity, and a good way to think about it is it's really the same set of atoms that you're using for the analysis. In contrast, a control volume is a volume in space through which a fluid may flow. It's geometric identity, and I've shown a diagram at the bottom of the page here. It's a jet engine, a little sketch of a jet engine that's moving through the sky. And I've shown a red dashed line around the engine, and that's the control volume that we're going to do our analysis on. And that control volume, or the outside of the control volume, is called the control surface, which I'm denoting as CS, is moving with the engine. So we've got flow in and out of our control volume, whereas if you looked at the mass in the engine at some time t1, at a few moments later, at time t2, that mass would have moved outside the engine. So from this simple example, you can see the difference between keeping track of a fixed parcel of matter, which is a systems approach, versus looking at flows in and out, which is a control volume approach. Now it turns out that the governing laws of motion are stated using a system approach. They're stated for a fixed quantity of mass. And if you think about F equals ma, when you used it in your physics course, that m was generally a fixed quantity of mass, a well-known quantity of mass. And also if you think about the conservation of mass principle, if you have a fixed amount of mass, as that fixed amount of mass undergoes changes, well, as the processes happen, the mass remains constant if we neglect relativistic effects. As I already mentioned, in fluid mechanics, we're more interested in drawing control volumes and looking at flows in and out, so we're interested most often in analyzing control volumes. And I've shown again here the example of a nozzle attached to a flange here over on this side, where we have flow in from the left and flow out on the right. And a typical application that we're going to do is calculating the force required to hold the flange in place. So you might do stress analysis to size the bolts. And to do that, we need to analyze the change in momentum of the fluid that flows through the control volume in addition to the forces on the boundaries of the control surface. So we need to rewrite F equals ma for application to a control volume. And the general method of relating a system to a control volume is called Reynolds Transport Theorem. And we're going to do that next. And I'll warn you, this gets a little bit heavy. The remainder of this video deals with the derivation of Reynolds Transport Theorem. And as I mentioned, RTT is the analytical tool that relates a system to a control volume. Before we can get into that derivation, I need to talk a little bit about thermodynamics. Now, this is going to be reviewed for mechanical and industrial engineers, so bear with this. We need to define two different types of properties. An extensive property depends upon the mass, or if you like, the size or extent of the system. So things like mass obviously depends upon how big the system is. Volume in cubic meters. Total energy would be another property that depends on the sort of the size or mass of the system. And then there's intensive properties. These are properties that are independent of the mass of the system. Things like pressure and temperature, they can be defined at a point. In addition to those, we have properties that are expressed on a per unit mass basis. Things like specific volume, that's the inverse of density, so it's how much volume per kilogram, or specific energy, which is how many joules per kilogram a substance might possess. So that's extensive properties and intensive properties. So now, for the purpose of Reynolds Transport Theorem, we're going to let this capital B be a sort of a generic extensive property for the fluid. So it might be the mass, it might be the momentum mv, or it might be the total energy. Now, I'm trying my best to use the same nomenclatures in the text, so you'll be able to relate this to what you read in the course textbook. In the course textbook, it then uses the symbol beta as being the corresponding intensive property. So beta is related to capital B in that beta equals dB dm. So for example, and I've rewritten the equation up here that relates the intensive property to the extensive property. So if we consider B to be mass flowing in and out of our control volume, then we're going to do our derivation in terms of beta, which is, in this case, beta would equal 1, because dm is 1. If we want to look at conservation of momentum, for example, we're going to use this generic property B as being mv. And in that case, if you take the derivative, you get beta equals just the velocity. And if we want to look at energy flowing in and out of our control volume, then little e is d capital E dm. So beta equals little e, the specific energy in joules per kilogram. So the analysis we're going to do is in terms of this beta property, which is a generic property that we can later substitute for any, well, these three in particular are of interest, but it could be substituted. We could use any property for B and its corresponding intensive property. Okay, now we've defined our generic property B and the corresponding intensive property beta. We can move on to derive Reynolds Transport Theorem. Now, your textbook has a general integral definition of Reynolds Transport Theorem, but I think for someone seeing this for the first time, it's actually quite difficult to follow. So I thought I'd start with a simplified derivation, and then after you've watched this video, you can go back and look at the more detailed derivation in your textbook, and it should be easier to follow. So to simplify the derivation of Reynolds Transport Theorem, I'm going to start with a simplified case. So we're going to consider one-dimensional steady flow through a stationary control volume. And I've shown in the sketch below, it's a variable area pipe, so it's expanding pipe. And we have one inlet and one outlet, and the flows are normal to the control surfaces. So the inlet over here, we're going to denote 1, and the outlet cross-section, we're going to denote 2. And in Reynolds Transport Theorem, what we're considering is a fixed mass, so a system, sweeping through the control volume, which is fixed in space. So the red dashed line is the control volume, which stays in place, and the black dashed line is actually the system, the fixed mass of a moment later. At time 0, or time t if you like, the system is coincident with the control volume, and a moment later, a little increment delta t, it's been swept to the right. It's carrying in property, intensive property beta 1 at cross-sectional, the cross-section 1, and it's carrying out property beta 2 at cross-section 2. So there are 3 sources of change of our arbitrary property B within the control volume. Now personally I find it helpful to actually think of B, even though B is a generic property, think of it as something specific. So let's think of it for the purpose of this derivation B to be momentum. So B is mv, and therefore beta would be velocity. So there is the rate of change of momentum, or B, inside the control volume, the time rate of change here. And this could be caused by forces at the boundaries. So the pipe may exert a force on the fluid and accelerate the fluid. So the actual fluid inside the control volume is changing momentum. And then there's in and out flows. And remember, we have inflow at cross-section 1 and outflow at cross-section 2. Beta is is the property per unit mass. We multiply it by m dot, which is mass per unit time. So beta 2 times m2 dot is the rate at which B is flowing in. For example, momentum is flowing out of the control volume at section 2, and beta 1 m1 dot is the rate at which property B is flowing into the control volume at cross section 1. Let me go back one slide just a moment to explain something before we go to the next slide. At time t, the mass inside the system that we're considering is coincident with the control volume. And then at time delta t, it's moved a little bit to the right. So what's happened here, and that's what this diagram here is about, is that the system initially occupied this area here. So it initially occupied the control volume, and then at time delta t, it's moved to the right, and now it occupies this volume. So this area, this little shaded area in here, is the control volume minus this little sliver of area, area 1, and it's gained this little area here. So it's lost area 1 and it's gained area 2 as it's moved to the right. So let's move forward now. So this is restating what I just explained, that at time t, the system and the control volume are coincident, and then at a small interval of time, the system loses this little sliver of area and gains this little sliver of area. So the new system position is the control volume minus area 1 plus area 2. So now in the limit, as that little increment in time goes to 0 and we take the derivative, we get the time rate of change of B into the system is, so the time rate of change of this property B, which might be momentum or energy or mass, is equal to the rate of change of that property B within the control volume in time, plus the outflow minus the inflow. Remember, beta is an intensive property. It's the property per unit mass times the mass per unit time. The mass flow rate gives you the rate of flow of, this is the rate of flow of B. So that's the outflow, and the second term is the inflow. And the system has gained this amount of outflow and lost this little sliver of inflow. So this result is for clearly for one-dimensional flow with one inlet and outlet. But we can easily generalize this. This result can be generalized for any number of inlet and outlet flows as follows. So in the general case, the total rate of change of B within the system, that's the fixed quantity of mass sweeping through the control volume, is the rate of change of B within the control volume. And keep in mind that the integral of B dm here, or sorry, beta dm, would be the total amount of B in the control volume. And then we add on the rate at which B leaves the control volume, and we subtract the rate at which B enters the control volume. And this is equation 3.18 in your textbook. It's the equation we're going to use most often in this course. You should keep in mind that it's restricted for a fixed control volume, so a control volume that's not moving in space or deforming, and it requires the assumption of one-dimensional flow with the flows being normal to the control surface boundaries. But nevertheless, it's a really handy equation. We're going to use it in this course, and we're going to use it most often with this transient term set to 0 because we're considering steady flows. So, for example, imagine we're trying to apply Reynolds Transport Theorem to the control volume shown on the right-hand side over here. I took this from your textbook. It has 5 locations where flow enters and leaves or leaves the control volume. And you'll note here that at section 1, flow's coming in, and at we have one other inlet. We have at section 4 here, flows coming in. And at section 2, 3, and 5, the flow's going out. So in this case, here's the general expression. Here's the general expression for Reynolds Transport Theorem. We're considering a steady flow, so we can set the transient term to 0. There's no rate of change of the property B within the control volume. So to get the rate of change of B of the system, we just have to add up the rate at which B leaves the control volume. That's beta 2 M2 dot, beta 3 M3 dot, beta 5 M5 dot, that's where the flow is going out, minus the inflows, which is beta 1 M1 dot minus beta 4 M4 dot. And we recall from the previous video that the mass flow rate can be expressed as rho AV, and we're using a one-dimensional flow approximation here, so we're assuming that the velocity and the property beta is uniform at each cross-section. We can simply express the result of Reynolds Transport Theorem. So for this control volume, the rate of change of B in the system can be expressed very simply. So far we've been assuming one-dimensional flow with flow that's normal to the control surfaces. I mentioned at the beginning of this video that there's a general derivation in your book of Reynolds Transport Theorem where we don't make that assumption. And it's done using the control volume shown below here. And if you go back and look at your textbook, I think you'll understand that, or it's possible to understand that derivation now more easily, having gone through the one-dimensional approach. So just for completeness, I show the general expression of Reynolds Transport Theorem for a fixed non-deforming control volume. It's shown here. It looks similar to what the equation we had before. the rate of change of B, this property B within the system, is equal to the rate of change of B within the control volume. And now we have the integral of beta times rho dV. That's the total amount of B within the control volume. And then we have the flux term at the boundaries. And that's the integral over the control surface of beta rho, and then the velocity vector dotted into the unit normal vector n. Notice that we don't have a separate inflow and outflow terms in this expression. Because n is the unit normal, when the velocity is crossing the boundary in the outwards direction, that last integral, the integral over the control surface, becomes positive. And when the flow is inward, you get a negative value because the unit normal points outward. And of course, the dot product gives you the component of the flux of B that's normal to the boundary. As I say, I include this really for completeness. In the remainder of the course, we're going to use this simplified one-dimensional equation, 3.18, and normally the unsteady term in our applications will be 0 because we'll be dealing with steady flows. There's one last topic I'd like to cover before we end this video, and that's the application of Reynolds Transport Theorem to moving control volumes. I've shown a situation below where you might want to use a moving control volume, and this is analyzing, say, the thrust from a jet engine. In this case, you set up a control volume, the red dashed line, that's moving with the engine. And so in this case, we write Reynolds Transport Theorem, but we need to use the relative velocity between the fluid and the control volume. So we have, on the left-hand side here, a flux of this property B into the control volume, but it depends on the relative velocity at the inlet between the fluid and the control volume. And similarly, we have a flux of this property B out of the control volume that depends on the relative velocity between the control volume and the fluid. And so the absolute velocity here will be equal to the relative velocity plus the velocity of the control volume. And of course, in some situations, you need to consider that in a vector sense. So now Reynolds Transport Theorem for a moving control volume with the usual one-dimensional flow assumptions becomes as follows. It's exactly the same equation, except you'll notice that the velocities here are the relative velocities at the inlet and the outlet, where the relative velocity VR is the relative velocity between the fluid and the engine. So you take the absolute velocity minus the control volume velocity. The textbook has some more detailed generalized derivations for things like moving deformable control volumes and non-inertial, in other words, accelerating reference frames, but we're not going to be covering those. You should check out the chapter summary for chapter 3 on the Blackboard. It explains in detail what you're responsible for. I realize that this video probably was fairly boring and maybe a little hard to follow, but it's important that you understand Reynolds Transport Theorem, at least at some level, because in subsequent videos we're going to apply it to the derivation of the conservation of mass equation for control volume, and then conservation of momentum, where we're going to calculate forces on control surfaces.